So we've been interpreting the output for a linear regression model. How do we know if that linear model is a good fit? One way is to use a residual plot. So there's a couple different kinds of these, and we'll see more in Unit 11. But for now, we're going to focus on a specific type of plot where on the y-axis you put your residuals. So in other words, the y-axis is showing the difference between your actual value and your predicted value, or the distance between the point and the line. And then on the x-axis, there's a couple different options. One is just to use the explanatory variable, so put your regular x variable on the x-axis, or another option is to do the predicted values on the x-axis. So that's your y-hat values. And either way, you're really looking for the same thing. So basically what this does, you can sort of think of it like taking your scatter plot and then turning it so that your prediction line becomes the x-axis, right? Because you want all of your points that are above the line, those are positive residuals, so they're going to be positive on your new plot. All the points that were below the line have negative residuals, they're going to be negative on your new plot. And once we have that residual plot, what we want to see is we just want the residuals to be randomly scattered around 0. So this one where we just have a random scatter of points is actually a good residual plot. This one looks good. What we don't want to see is something like this where we have a distinctive curved pattern. That would indicate that you have a non-linear relationship, right? So here there's negative residuals on the extreme ends of the axis and positive residuals in the middle. So that would mean that you are overestimating for the points that are at the ends of the x-axis and you are underestimating in the middle. We expect there to be some sort of random over and underestimation, but we don't want it to be systematically overestimating or systematically underestimating like it is in this nonlinear situation. Another problem that you can run into is like this third one where we have non-constant variance. So the problem here is that if you look on one end of the axis, your spread around the line is very small. So I'm looking at like the vertical spread here. So that means that on one end, we have very precise estimates. If we think about our line as a way to predict the outcomes, they're pretty much falling close to the line on the low end. But then here on the high end, it's much wider, much less precise. And so a problem with this is like if you're thinking about your R squared as like how much variability is explained, how accurate are your estimates, well, it kind of depends on where you are on the x-axis, right? For some x values, it's very precise, and for others, not so much. So when we look at our residual plots, we're checking for linearity, and we're checking for constant variance. So let's go back to this Honda Civics data that we had before. And earlier we had done a linear regression model, so we just did analyze fit y by x, and we put the price as the response and the age as the explanatory. And to get the regression line, you do fit line. If we want to plot the residuals, we go down here where it says linear fit, and we're going to choose plot residuals. So there's several different options here. For now, we're going to focus on just using either the residual by predicted plot or the residual by x plot. Both of those are read basically the same way. So looking at this, I don't really see either of the problems that we were concerned about. I don't see any kind of curved pattern here to be worried about. I also don't really see any kind of like funnel shape or fan shape like we saw in the other example. It's a little bit different on the low and the high ends, but also if you notice like 7- and 8-year-old cars, there's only a couple of them in the data set, so it's not really surprising that the spread is a little bit smaller there. So looking at this residual plot, I wouldn't see any problem with using a linear model in this situation.